This video is about calculating freezing point depression and boiling point elevation based on colligative properties. Okay, so if you're not familiar with colligative properties, you may want to go back and watch the intro video on what colligative properties are, but just kind of as a quick recap, colligative properties are properties of a solution that depend on the number of particles dissolved, and that'll do two things. It will elevate the boiling point and it'll depress the freezing point. What we're going to be going over in this video is we're going to learn how to do the calculations. And so the first thing that we need to do is we need to understand the equation. The equation for calculating freezing point depression and boiling point elevation is delta T equals I times lowercase m times K. Delta T, remember delta means change. So the change in temperature equals I is what we call the Van't Hoff factor or the ionization factor. M, lowercase m, remember, is molality, and molality is found by taking the moles of solute divided by kilograms. And then finally K. K is a constant, and there's the Kf and the Kb. Kf is when we're dealing with freezing point, and that constant is 1.86 degrees Celsius per molality, or lowercase m. And then there's Kb. Kb is for the boiling point, and that would be 0.52 degrees Celsius per molality. Alright, and so that is our equation, and we're going to refer back to our equation several times. Now remember, I is the Van't Hoff factor, and that I, or ionization factor, is based on the idea of electrolytes and non-electrolytes. In our introduction video, we talked about electrolytes being ionic compounds that split up in water into parts. Non-electrons were covalent compounds. They stayed together, and this number of particles is what we call the Van't Hoff factor, and that's very important because the higher the Van't Hoff factor, the higher the colligative change we're going to see. Alright, so let's look at a couple of examples. We're going to go through 4 examples, and then in the next video we'll go over a couple of homework problems. And we're going to make sure that we are focusing on the idea of delta T equals I times M times K. Okay, so here's our first problem. Our first problem says, what is the new boiling point of a CaCl2 solution with a molality of 1.5 lowercase m. Okay, so let's start by just writing on the top of our paper here. We're going to write our equation. Delta T equals I times M times K. And we're going to go in and we're going to kind of read our problem and see what we're looking for. We're looking for the new boiling point. So that means that I'm going to be looking for Kb. And I have CaCl2, and it has a molality of 1.5 m. Well, I know that a molality of 1.5 m, that's going to be m. So, if I'm going to look for the new boiling point, I'm going to be looking for delta T. So, I'm going to know that delta T equals I times m times Kb, because I'm looking for boiling point. Well, as I saw before, my Kb is a constant, and so Kb is going to be 0.52 degrees Celsius per m, always, whenever we're dealing with boiling point for water. So for K, I can put in 0.52 Celsius per m. My molality was given to me 1.5 m. And so now I just need my I, or my Van't Hoff factor. Now I know that my Van't Hoff factor is based on what CaCl2 will break into. So I look up calcium, I see that it's a metal. Cl2 is a nonmetal, so that's an ionic compound. And so that means I'm going to get 1 Ca and 2 Cls. Well, 1 Ca and 2 Cls, Ca, Cl, Cl, that makes 3 particles. So my Van't Hoff factor, or I, will be 3, because that tells me how many parts it ionizes into, or breaks into. So now I just need to cancel out my m's, and I'll be left with degrees Celsius, which is what I want. So let's calculate that. We're going to take 3 times 1.5 times 0.52. And what we get from that is 2.34. We're just going to double check that calculation. 3 times 1.5 times 0.52. We get 2.34 degrees Celsius. Now this is my change in temperature. The problem asked me for the new boiling point. Well, I know that water typically boils at 100 degrees Celsius. And by adding a solute, I'm going to increase or elevate the boiling point. So that means I would add 2.34 degrees Celsius to it, and my new boiling point would be 102.34 degrees Celsius. It would be elevated because of the amount of solute that I put into it. Alright, so let's look at another situation. Similar, but we're going to see if there's a different impact. Okay, so our second question says, what is the new boiling point of a C6H12O6 solution with a molality of 1.5? So again, delta T equals I times M times KB. I know it's KB because it said boiling point. My I is my Van Hoff factor. Well, C6H12O6. Carbon is a nonmetal, hydrogen is a nonmetal, oxygen is a nonmetal. Since those are all nonmetals, it's a non-electrolyte. And so it's not going to break up. So it's going to have a Van Hoff factor of 1 because it's going to stick together in water. Times M. My molality is 1.5. And my KB, remember that's a constant, and that constant is 0.52 degrees Celsius per molality whenever I'm talking about boiling. Okay, so my molalities cancel. It's now I just have 1 times 1.5 times 0.52. And so when I type that into the calculator, 1 times 1.5 times 0.52, and I get an answer of 0.78 degrees Celsius. That was my delta T. It asked me for the new boiling point, so I do my math over on the side. I know that the regular boiling point for water is 100 degrees. Since I've added something to it, it's going to increase the boiling point by 0.78 degrees, and so I get 100.78 degrees Celsius as my answer. So let's take a second and let's compare what we had happen. Although we had the same molality and we were dealing with boiling points, we got two very different answers. Why did we get such different answers? Well, it came down to I, or the Van Hoff factor. For CaCl2, the Van Hoff factor was 3. And so that 3 gave us, when we put it into the equation, 2.34. In the second equation, our Van Hoff factor was only 1 because C6H12O6 didn't break down. It remained as one particle. So then our answer was 0.78 as a change in temperature. So we know that a non-electrolyte will have less of an impact as an electrolyte when put in as the same molality. Okay, so now that we have looked at our equation, we know that delta T equals I times M times K. Delta T is the change in temperature. I is the Van Hoff factor, or how many particles it breaks down into. M is molality, and K is a constant. Let's look at one where we're dealing with freezing point. Okay, so it says, what is the new freezing point of an NH43PO4 solution with a molality of 0.75? So I know delta T equals I times M times K. This time it's going to be KF because we're dealing with K, the freezing point. So let's look at my I. My I is my ionization factor. NH4, that's on the back of my periodic table, that's a polyatomic ion. So is PO4. Since they're polyatomic ions, I know they're going to break into parts. I have 3 NH4s. So NH4, 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 and then I have a PO4. Now, it's really important to notice that the polyatomic ions, they did not split up from each other. They remained just as I would see them on the back of my periodic table. But this compound as a whole would break into 1, 2, 3, 4 parts. So my Van Hoff factor is a 4 times my molality, which was 0.75 from the problem. And then I have to get KF. Remember, KF was a constant. The constant for freezing is 1.86. So 1.86 degrees Celsius per molality. Type that into my calculator, and I'm going to get 4 times 0.75 times 1.86. When I put that into my calculator, I get 5.58 degrees Celsius. Because my molality cancels. But then I have to think, this is only my change in temperature. Well, what's my normal freezing point for water? My normal freezing point for water is 0 degrees Celsius. I know whenever I add a solute, it's going to decrease or depress the freezing point. So I'm going to have to subtract my change, 5.58 degrees Celsius. That means my new freezing point would be negative 5.58 degrees Celsius, 0 minus my change. And the reason I had to subtract in this problem is because it was a freezing point, and I know that it's always a freezing point depression. It's going to lower the freezing point. With the boiling point problems, I had to add because it's boiling point elevation. So the boiling point had to go up from the normal. With freezing point, it's going to go down from the normal. Okay, let's look at one more question that makes it a little more difficult. It's kind of a challenge problem. And it's just because it's going to require us to do a little bit of work. Okay, so it says find the change in boiling points of a solution made by adding 45.7 grams of potassium sulfate to 750 milliliters of water. Okay, so I know that I'm going to have delta T equals I times M times KF, but I'm going to have to do some work in order to get this information. Okay, so let's start with I. I is going to come from potassium sulfate. So potassium sulfate, potassium is K plus 1, sulfate is SO4 negative 2. Well, plus 1, negative 2, I'm going to need another K in order to make that balance. So it's going to be K2SO4. So I can see 1, 2, 3. It's going to break into 3 particles. So my Van't Hoff factor is going to be 3 because it broke into 3 parts. Remember, my polyatomic ion does not separate from each other, but it does separate from the other ions in the compound. So 3 particles. Now I need to find my molality. Molality, remember, is going to be moles of solute divided by kilograms of solvent. I have the information in my problem to do it, but it's going to take me a little bit of time. Okay, solute is the thing that's being dissolved. Well, when I read my problem, I know that I'm adding 45.7 grams of potassium sulfate. So that must be the thing that's being dissolved. So I need to turn that into moles. So 45.7 grams of K2SO4, because I've already found my formula. Since grams is on the top, it's going to go to the bottom, K2SO4, and we've got moles on top. 1 mole equals the grams from the periodic table. So we're going to quickly get the grams from the periodic table. We've got 39 times 2 for potassium, plus sulfur, which is 32, plus 4 times 16 for oxygen. So that'll be 16 times 4, we got 64, plus 32, plus 39 times 2, which is 39. So I get 174 grams for potassium sulfate. So when I take 45.7 divided by 174, I get 0.26 moles of K2SO4. So that's going to go up here, 0.26 moles, and I have to divide it by kilograms of solvent. Well, my problem gave me 750 milliliters of water. Well, I know that a milliliter and a gram are the same thing when we're talking about pure water. So really I could just say that I have 750 grams of water because I need this to be in kilograms, and grams is the closest thing to that. Well, if I divide grams by 1,000, my grams by 1,000, I'm going to get kilograms, and so I get 0.75 kilograms. So I have 0.75 kilograms. So I'm going to take 0.26 moles divided by 0.75, 0.26 moles divided by 0.75 kilograms, and I get a molality of 0.35 lowercase m. So that's going to go up here in my problem for molality. 0.35 molality times KB, because I needed to know the boiling point. So it's going to be KB, and the KB constant is 0.52 degrees Celsius per molality. My molalities cancel, and so I take that and put that in the calculator. 3 times 0.35 times 0.52, and the answer that I get is 0.546, and that would be degrees Celsius. Now it was boiling point, so I know my normal boiling point is 100 degrees Celsius. I have to add 0.546 degrees Celsius to it, and so my new boiling point is 100.546 degrees Celsius.